Good morning, everyone, and welcome to today TSU PRISM and the AOGS RSC CGWG joint online seminar. So today we are very pleased to have the Dr. YangChou from the NASA Goddard Space Flight Center with us today. So Dr. Chou is an ionosphere thermosphere scientist at the CCMC with the expertise in atmospheric wave and their impact on the ionosphere. He has worked extensively with the Formosat 3 and the Formosat 7 mission, and currently support the ionospheric modeling and the validation at the NASA. So today's talk is the title, Space Weather from the Earth, Impacts of the Tsunami and the Convectively Generate Gravity Wave in the Ionosphere. Dr. Chou will share how the events like the 2011 Tohoku tsunami and several weather systems can generate gravity wave and disturb the ionosphere, sometimes even cross the hemispheres, and how this disturbance relate to the space weather effects such as the equatorial plasma bubbles. So let's give a warm welcome to Dr. YangChou. Professor YangChou is yours.
Okay. Hello, everyone. My name is YangChou. So can you see my screen?
Yeah, it's clear. It's very clear.
So I'm YangChou. I'm actually from Taiwan. So it's my honor to have this opportunity to share my work at TSU. So today, I'll talk about the space weather from Earth. So this work is mainly done when I was a postdoc at UCAR Cosmic Program Office, and also at CCMC, I'm also working on some bubble studies. So we have to understand how this tsunami and the convective generate gravity waves on the ionosphere. So of course, I need to thanks for my supervisor, previous PhD supervisor, Justin's support, and also my colleague, Jia Yue and Joe Huba. Without their support, I cannot finish this work. And of course, all other colleagues from UCAR and NASA and IL. So before giving this presentation, I would like to advertise our CCMC. NASA CCMC actually is a community coordinated modeling center. So we provide a great number of models from the sun to the ionosphere and thermosphere. So if you are interested in using these models, you can use our service. It's very easy that you can just submit a request from our website, and we will run a model for you, so you can use our modeling results to your research. So you can see that there's so many models. So based on these models, I'm talking about the space weather. And the space weather linked to forcing from above and below. So I think most of them are students. I think you guys probably know that space weather. The definition is that it refers to the solar and the geospace conditions that can greatly impact our humans' technology and human health. So we always think that sun should be the primary driver of a space weather. So it greatly impact our ionosphere. We care about ionosphere. One of the most important reasons that we have so many satellites in the ionosphere, and also ionosphere is the major air source of the GNSS positioning and navigation. So it's very important to understand the variability of the ionosphere. But I think over the past decades, we always thought that the sun should be the only driver. But over the last decades, we understand that actually there's another branch of space weather that's originated from below, from our terrestrial weather on Earth. So here just shows an example that that we know that the sun can greatly impact our ionosphere, but the weather system like sunstorms and actually they can also generate waves and propagate upward into the ionosphere, so cause very significant day-to-day variability. So it's very important to understand how these waves cause variation in the ionosphere, because we, as I mentioned, that we highly rely on our satellite and the GPS GNSS navigation system. So I think this figure just shows an example that it illustrates how those forces from the lower atmosphere, propagating upward to the mesosphere and the ionosphere, then impact the the ionosphere. So there are many sources that actually can. Yeah, the waves they can like there are different kind of waves, like gravity waves, tides, and planetary waves. They have different spatial and temporal scales. But in this study, we are focusing on the gravity waves that has relatively smaller periods and wavelengths. So gravity waves actually can generate by different sources, like in the equator, we have convection. This convection can generate gravity waves propagating upward and to the ionosphere. But one of the most important space weather phenomena is here is the bubble. So this gravity wave actually can see these plasma bubbles, and this is very important because it can cause the loss of luck of our GPS signals. So we always want to understand what's the underlying physical mechanism to trigger these plasma bubbles. And gravity waves appear to be a very important role to see these bubbles. So today I will talk about this. And also, we also have like a type, like ocean waves, mountain. This also can generate gravity waves and propagating in the ionosphere. So gravity wave propagating in the ionosphere or atmosphere, we can call it like a traveling ionosphere disturbances or traveling atmosphere disturbances. So you can see that they are very complicated systems. So it's very challenging to understand the physics. One of the reasons that we do not have sufficient observations. So we usually rely on like models and observations to address these complex questions. So I think there are, as I mentioned, there are different kind of source that can generate gravity waves and propagating in the ionosphere and cause traveling ionosphere disturbances. So this figure just shows example from the U.S. Department of Defense, DARPA. So I think that atmosphere can be a sensor to sense different wave sources. For example, like an audience on thunderstorms, nuclear explosions, or rocket launch, tornado, or hurricane, or blast, meteor, Tohoku earthquake, volcano eruptions. So you can see, you can cause some ionosphere perturbations, and here also shows the equivalent TNT energies here. So from this figure, we can understand that atmosphere actually can be a sensor to detect like missiles or rocket launch, everything. So yeah, here just shows some example that this is from the Nishioka's paper that showing that we use the ground-based GNSS receivers over the US to detect the tornado-generated concentric gravity waves in the ionosphere. So you can see very clear concentric patterns here. And also, yeah, I think this should be the first paper that reported the convected general concentric waves in the ionosphere. And in addition to this tornado, we also have a man-made source, like Falcon 9 rocket launch. This is Professor Charles Lin's paper. We did this when I was a PhD student. So this is the first time we found that rocket launch actually also can generate concentric gravity waves in the ionosphere. And this is a Tonga volcanic eruptions that occurred 3 years ago. It's displayed very distinct traveling TID and propagating across the globe. And also the super typhoon Miranda shows for the first time we observed the typhoon-induced concentric gravity waves in the ionosphere. So this work was done when I was a PhD student. So, but today I would like to focus on the Tohoku event. I think just a schematic used to explain how this Tohoku earthquake and the tsunami triggered traveling ionosphere disturbances. So you can see that we can use like a GPS GNSS satellite, and when these GNSS signals transfers to the ionosphere, and we can detect these wave perturbations. So earthquake actually can generate some acoustic waves, and also the tsunami can generate gravity waves with different temporal and spatial scales. And these perturbations can perturb the ionosphere, so cause some perturbations in our GPS TC signals. So here just shows an example that this is an observation of GNS-TEC. So the blue line here shows the absolute TEC, and the red line here shows the filter, the TEC. We remove the background trend, so you can see more clear perturbations. So yeah, if we use the GPS satellite, we can observe this kind of signatures and remove the background trend. You can see more distinct and significant perturbations related to gravity waves. So we can use this technique and to detect all the waves from below or from above. And I think this is the Tohoku earthquake. It's occurred almost over 10 years ago. So when I first see this figure, I think I was very surprised because during this time I was like a master's student, and this is my first time I saw this. Wow, why this earthquake can generate such beautiful waves in the ionosphere? I was very surprised. After that, I was fascinated about this work. So I can show you that this is a magnitude 9.1 earthquake. So you can see that when the earthquake happened, it shows very distinct concentric gravity waves. And so I think this is the snapshot of the concentric waves driven by the Tohoku earthquake and tsunami. So at first, you can see that earthquake actually can generate acoustic waves. So you can see that this wave propagated very fast, much faster than gravity waves, and that they have shorter periods. And then following the earthquake acoustic wave, you also can see that like a tsunami induced a concentric wave. The concentric waves, are gravity waves that are have smaller horizontal scales. You can see here, and also you can see very distinct concentric wave emanating outward. Interesting is that you also can see that radio waves, seismic waves, you probably get around like 2,000 kilometers to 3,000 kilometers per second. So it's very fast, and this fast wave actually triggers the acoustic waves and perturb the ionosphere. So yeah, this is just some background about the Tohoku earthquake. So what I have done is that we also noticed that we know that this tsunami actually can propagate very long distance. So this is a simulation, tsunami simulation done by NOAA. So you can see that this tsunami actually propagated very long distance across the Pacific Ocean. So some previous studies shows that when this tsunami reached the Hawaii, they used the air-ground imagers to detect these perturbations. And also in the United States, we also have ground-based GNS TEC. So you also can see very clear TID here. And when this tsunami eventually reached the South America, so there's also air-ground imagers that can capture these perturbations. So we can understand that actually this tsunami has very significant impacts on our Earth's ionosphere. But I think the most important part is that you can see that this is from McKenna's work. They use the air-ground imagers over Hawaii to detect this tsunami waves. But interestingly, you can see that actually these ionosphere perturbations, TID, are probably ahead of these tsunami waves. The tsunami ocean waves here were indicated by these red lines. So you can find that actually in the ionosphere, the TID is propagating much faster than the tsunami ocean waves by about 1 hour. So this demonstrates that the ionosphere actually can potentially be a tool for tsunami detection and early warning. So that's the reason that we want to use the ground-based GNS network to do some tsunami early warning system. And I think particularly interesting is that when this tsunami wave propagating across the Pacific Ocean, you also can see very clear refractive waves So you can see very clearly, see again, these reflective waves are reflected by those seamounts and ridges, and then this reflected tsunami wave propagating backward toward Japan. So when we use the ground-based GNSS-TC over Japan, we also can see identify very clear reflective waves here. So this reflected tsunami waves also trigger like planar gravity waves and propagating upward to the ionosphere. So you can see that it's just very distinct waves. So yeah, next, this is a snapshot that's showing that if we compare the TID with the ground, like the tsunami ocean wave, you can see that here you can see that we call this MSTID is propagating like a southwestward. And if you compare the tsunami from this is from Tang et al. Model simulations, you can see that the wavefront and the horizontal scales are nearly identical. And also you can see some like a smaller scale tsunami. And in the ionosphere, you also can identify very similar wave structures here. And here also you can see that it's just some concentric wave patterns here. And we also can identify the same wave structures in the ionosphere. So the ionosphere, the TID almost reflects the structures of the tsunami waves. So this is pretty interesting that we've observed this for the first time. And I think the most interesting part is that even 2 days after the Tohoku earthquake, we also can identify this tsunami. This is a reflected tsunami reflected from the South America, and it took about 2 days for this reflected wave propagating backward to Japan. So in the meantime, we use the ground-based GNSS-TC here. You also can see this reflected wave shows very similar structures. So because we know that all the ground-based GNSS receivers, they are only limited to the continents. So we try to use the Cosmic 3, Formosa 3 Cosmic is a Taiwan satellite. So I want to understand if Cosmic can detect those tsunami waves. So here that shows the trajectory of the Cosmic observations. So you can see that there are 8 profiles, and here I showed like here the blue line here indicate the observation during the Tohoku earthquake event day, and red line here indicates the reference day. So you can see that the solid blue line here indicates the filter, the TEC. So you can identify very clear significant perturbations here and for these observations, and also here. So if you compare with the reference date is the red line, you can see that the reference date, the perturbation is much weaker compared with the event date. So these perturbations are most likely related to the Tohoku tsunami-induced gravity waves. And we also can use the wavelet spectrum to wavelet analysis to analyze the vertical wavelengths. So you can see that the vertical wavelengths of these perturbations are around like 100 kilometers. So this is pretty similar to comparable to the characteristic of the tsunami-induced gravity waves. So I also need to mention that, as I mentioned earlier, that Makela et al. He first shows that the tsunami-induced TID can precede the ocean tsunami by 1 hour. So we would like to know what's the underlying mechanism why the tsunami-induced TID can propagate much faster than the tsunami itself. So I think this is from the Itchins et al. So he's now working at MIL. So he used a model to conduct some model simulations. So he's trying to understand why the TID can propagate much faster than the tsunami. So here it shows some simulation results that you can see that here's just some tsunami waves, and we can focus on this part. You can see that these waves actually can generate a broad spectrum of gravity waves and propagating upward. And for those leading waves, actually they are Doppler waves, so they have shorter vertical wavelengths, and they are propagating much faster than those short period waves. And the short period waves, they can more propagate more vertically. So the long period wave propagate much faster. So this can be the reason why we can observe these leading waves, because they are long period waves. So you also can notice that these long period waves have a vertical wavelength of about like 100 kilometers. This is also comparable with our cosmic observations. It also shows that the vertical wavelengths are around 100 kilometers. So this explains why the TID is faster than tsunami. So, but we want to confirm that those observed TID are related to the tsunami. So we compare the TID observations with DART. DART is the buoy that measures the ocean wave perturbations. So the top panel here that shows the DART observations. So this is the water height. So you can see that it shows very clear fluctuations related to tsunami. And we also use the weather spectrum here to analyze this DART ocean wave perturbations. So we can see that it shows very large perturbations here. And these perturbations have periods around 30 to 50 minutes. And following that, you also can see very clear enhancement here and here with a relatively shorter period, around 30 minutes. And if we compare with the ground-based GNST observation here, so here just shows the kilograms of the TID. It's a function of UT time and the distance. So you can find that the TID shows in wear amplitude enhancement here and here and here. So this is pretty comparable with those DART observations. But we can notice very significant time delay is about like 1 to 1.5 hour delay between these three peaks and these three peaks. So, but this is reasonable because we know that this tsunami generate gravity waves usually take about like 1 hour propagating to the ionosphere from the ocean surface. So we also can notice that the tsunami actually the wave period is longer than those TID. The reason is that as I showed from previous slide, that the tsunami usually can excite a broad spectrum of gravity waves. And this TID are most likely related to the short period waves because they had longer vertical wavelengths and stronger amplitude that can penetrate to the ionosphere without severe dissipation. And the long period waves actually is very difficult to be observed because the vertical wavelength is smaller, so the wave amplitude is relatively weaker. So, but we should expect that those long period waves can propagate ahead of those tsunami waves. So next, I will talk about something interesting is that we observed the reflected tsunami wave propagating toward Japan. So you can see that this is a reflected tsunami waves, and they keep propagating southwestward and toward Japan. And in the meantime, we use the ground-based GNST observations over Japan and Australia, and we find very similar signatures. We call this conjugate effect. So you can see the movie here. So yeah, around around 11 UT, you can see there's some perturbations here, and then you can see these MSLD structures appear here. This is related to these reflected tsunami waves. In the meantime, if you compare the observation here with Australia, you also can identify very clear TC perturbations here. So, and in the southern hemisphere, this TID mainly propagate southwestward, and northern hemisphere is northwestward in southern hemisphere, and then southwestward in the northern hemisphere. So we call this this is related to the conjugate effect. So I can show you the snapshot here. I think it will be more clear. That top panel here shows the MSTID propagation at different UT time. So you can identify here shows the very distinct MSTID structures related to the reflected tsunami waves. And also here, you also can identify very clear conjugate MSTID fluctuations. So of course, you may mention that it's not very clear because we do not have sufficient data coverage. So we examine the single station here. So this slide just shows we select like 4 GPS receivers over Japan and 4 GPS receivers over Australia. And here just shows the TEC observations over Japan and Australia. The blue line here is the absolute TEC, and the red line here shows the filter TEC. We use the bandpass filter to remove the background trend. So you can identify very clear like N-shaped features here. And this N-shaped feature will and then keep propagating like southward. So in the meantime, you also can identify these N-shaped features here. So it is nearly identical to each other. But if we examine this the amplitude, you can find that in the northern hemisphere, the amplitude of this TC fluctuates around like a 1 to 2 TCU, and periods around 20 to 50 minutes. But in the southern hemisphere, the TC perturbations have weaker amplitudes of about like 0.5 TCU, and periods are very similar. So I think this is the first time we can observe that tsunami not only can cause perturbations in the northern hemisphere, actually it also can cause perturbations in the southern hemisphere through the conjugate effect, inter-hemispheric coupling process. So this slide, I want to explain how tsunami in the northern hemisphere like cause conjugate hemisphere perturbations in the southern hemisphere. This is work was done by Joe Huber in 2015, I think, and this work here I show was published. This work was published in 2022. So I think after 7 years, we finally found evidence to support this simulation work. So from Joe's simulation work, he mentioned that gravity waves actually it can cause neutral wind perturbations. And these neutral wind perturbations in the northern hemisphere and also can cause like ion velocity perturbations along the field line. So you can see that this perturbation only occurred in the northern hemisphere. So we call this ion neutral coupling process. But the gravity wave propagating in the ionosphere also can impact the background neutral winds. So it can cause the neutral wind perturbations. And these neutral wind perturbations will eventually induce electric fields. Because ionosphere field line is very conductive, so highly conductive. So once the electric field generated in the northern hemisphere, it will transmit along the field line to the conjugate hemisphere. So you can find these electric field perturbations along the field line. And this electric field perturbations will eventually lead to here's just electron density perturbations through the E-Crosby drift. So we call this electrodynamic coupling process. So this is the theory that used to explain why the tsunami can generate gravity waves, can cause this conjugate effect in the conjugate hemisphere. So yeah, so this is probably all the tsunami work. And I also need to mention that in addition to tsunami, there's another different source that can generate gravity waves. So I think this is a very popular figure from Jeff Dye, that he's a photographer that he captured this very beautiful concentric rings. Yeah, in the meantime, NASA's Tsunami satellite also can capture this very clear concentric rings in the mesopost region. So this is the gravity wave seen from below and seen from above. And these gravity waves are mainly generated by the thunderstorms. And thunderstorms, actually, their gravity waves, they can generate gravity waves, and they are ubiquitous. They occur very often. Unlike the tsunami, maybe only occur like once per 2 years or 3 years, but thunderstorms generate gravity waves almost occur every day. So it has more significant impacts on our space weather. So what's what's those convective gravity waves impacts on space weather. So yeah, sorry, I also need to mention that in addition to the convections, this is a super typhoon Mirandi that when this typhoon, I think this typhoon occurred in 2016. So this typhoon swept over Taiwan, so it generated very significant concentrated rains in the ionosphere, and this is captured by the streaming satellite. And we use the ground-based GNSTC, so you also can identify that it shows very clear perturbations. And I want to mention that this convection general gravity waves are very important because it can trigger plasma bubbles. So, so what is plasma bubble? So I think this is the images captured by the NASA Gold mission. So it shows an example of the plasma bubbles. So we can, from this figure, we can identify that there are two bands. We call this equatorial ionosphere anomaly, EIA structures. And within the EIA structure, you also can identify very clear dark bands embedded within this EIA structure. So we call this bubbles. And bubbles, what is very, I think it perhaps is one of the most important space weather phenomena because many occurred in the equatorial region in the nighttime. So because it greatly impact our GNS navigation and communications. So we always want to understand what's the underlying mechanism to trigger these bubbles. But currently, we understand that the radiator instability is a primary mechanism to trigger these bubbles. But the question is, what kind of a source that can facilitate the radiator instability? And you also can see that this bubble shows very significant day-to-day variability. Here it shows 4 consecutive days from like November 20 to November 23. So from previous work, we think that the reversal enhancement of vertical drift could be the primary driver of the plasma bubbles because this bubble usually occurs during the post-sunset period. So what is reversal enhancement? I think this here I show an example that this is from the II model. And this is a vertical drift as a function of local time. So during the sunset period, you can notice that here shows very significant enhancement of vertical drift. We call this a reversal enhancement. So this vertical drift will like push the ionosphere to very high altitude. So the ionosphere will become unstable. Then the bubble can be generated. However, this reversal enhancement actually cannot well explain the morphology of plasma bubbles in detail. Also, it cannot well explain the spatial distribution of these bubbles. For example, you can see that these dark bands show some periodic distributions here and here, but the reversal enhancement alone, it cannot really explain these kind of features. So the Tsunoda, he's like a Japanese scientist. So he proposed an upwelling paradigm to further explain the bubble development. So again, why do we care about plasma bubbles? So I think this is a very interesting story. The story is, of course, is because from the title you can see that it shows that the space bubbles may have led to deadly battle in Afghanistan, because this U.S. armies, they failed to receive the GNS signals, and because of the bubble disrupt the signal, the GNS signal, so it caused very huge impact, and it caused many people dies. So, but it's very difficult to, I think it's almost impossible to mitigate the plasma bubbles. So, but we want to understand when bubble will be occurred, so that we can prevent this kind of event happen again. So we need to have the sufficient knowledge. So that's the reason we want to study the plasma bubbles and understand what's the underlying mechanism to trigger bubble, so that we can forecast it. So this is the mechanism proposed by Tsunoda. We call this upwelling paradigm. So what is upwellings? This here just shows two figures, the ionosphere observations. This is observed by incoherent scatter radar from 2 different days. So this is electron density as a function of, I think, distance and altitude. For this day, this is near sunset time, so you can identify very clear that there are 2 lines here. It shows the slope. So this means that ionosphere, the uplift of the ionosphere due to the preversal enhancement. And this is in the other day, you also can see the uplift of the ionosphere due to the preversal enhancement. But the difference is that during this day, you can see very clear bottom side ionosphere undulations. So we call this upwelling structures. Based on this paradigm, we think that the bubbles actually can develop from the crest of these upwellings. And this upwelling can well explain the morphology, the structures. But this upwelling structures actually is very difficult to be detected because it's nearly stationary and it's located in the bottom side F layer. There's almost no observations to capture this kind of no satellite observations at this altitude. So we always need to have like a continuous distribution of ground-based instruments to detect this kind of structure. But the other question is that if these upwelling structures are the primary driver of plasma bubbles, so what's the source to drive these upwelling structures? So I think the most plausible source is gravity waves. So because their spatial scale, their wavelengths are usually comparable with gravity waves. So this is the, so I think we propose a gravity wave wind dynamo mechanism to explain why gravity waves can generate these upwelling structures. As I mentioned, that gravity waves, here just gravity wave perturbations, neutral wind perturbation, is the upward wind, downward wind, upward wind, downward wind. So the gravity waves can cause these neutral wind perturbations. And these neutral wind perturbations can induce like a diagonal current through the U cross B. And so you can, the yellow arrows here just shows the direction of dynamo currents. And these currents will also induce like a polarization electric fields to satisfy divergence J equals 0 in the ionosphere. So this E cross B drift will then eventually like push the ionosphere upward and downward, so leading to the development of upwellings. And bubbles will then develop from the crest of these upwelling structures. And but this is a hypothesis, but we have like satellite observations here. So this is the CNAV satellite in the, I think around like 600 kilometers or 400 kilometers. So here shows the bubbles. This is a vertical drift as a function of local time. So the red color here indicate the presence of plasma bubbles because it can cause very significant vertical drift enhancement within the bubble structures. But before the bubble development, we can also see very clear electric field perturbations. So maybe is this perturbations related to the gravity waves? We don't know. So we want to confirm that if this perturbation may be related to gravity wave, we try to use our models. So I think this is the RECOM-X model. We call this the whole atmosphere community climate model with thermosphere and ionosphere extension. So this is developed by NCAR. So I can here shows the movie that is used for study the gravity waves, tides, and understanding how these waves impact the ionosphere. So this is a model simulation. You can see very clear and distinct concentric gravity waves excited by all the convections. And here shows the typhoon. Here, a super typhoon generate concentric gravity waves in the ionosphere. So we can use this model and couple with another model we called SEMI3. SEMI3 is the model name is SEMI3 is a model of the ionosphere. It's a 3D physics based ionosphere and prospect model. It's developed by Dr. Joe Huber. So he's in at NASA and CUA. We are colleagues. So with the input from the webcam mask, so SEMI3 can self-consistently generate plasma bubbles. So currently, SEMI3 is the only model that can simulate global plasma bubbles. So here that shows the simulation result. This is just an example that it shows the TEC, and this in Taiwan. This is during the 2024 Maidstone events. So you can see very clear bubble structures here. You can see again here. So it causes very clear plasma depletions. So yeah, with the input from webcam mask, we try to understand how those gravity waves trigger plasma bubbles. So this is simulations on October 24, 2020. So the top panel here shows the electron density as a function of longitude and altitude. The bottom panel shows the zonal wind perturbations associated with gravity waves. So you can see very clear wave perturbations, neutral wind perturbations. And then you can see very clear, we call this upwelling structures are developed in the bottom side of layer. And then these perturbations eventually lead to the development of plasma bubble. And then it's during daytime, so all the bubbles were gone. So yeah, so it seems like these bubbles are related to gravity waves. One of the reasons that you can see that the zonal scales of these bubbles are nearly comparable with the zonal scale of these gravity waves. So next, we further examine the gravity wave neutral wind perturbations and the vertical e-cross-speed drift. So here that shows the new vertical wind perturbations as a function of longitude and the UT time in the ionosphere. I think it's around like 350 kilometers high. So this is the vertical wind perturbations, and this is a zonal wind perturbations. So you can see that it shows that during around like the breadth around 0 to 6 UT, you can see very clear wave perturbation, that this wave is very propagating westward here. And if we compare this neutral wind perturbation with the vertical e-cross-speed drift here, you can see that this wave shows very similar patterns here. The vertical e-cross-speed drift also shows similar wave structures. So this demonstrates that these vertical e-cross-speed drift perturbations are related to these neutral wind perturbations. And eventually, these perturbations lead to plasma bubbles. So you can see that it shows very significant or large e-cross-speed drift perturbations. But you also can notice that here shows the local time here from 1530 to 1930. And this is the daytime. But during the daytime, you can see that the wave patterns, the vertical e-cross-speed drift patterns are totally different from the neutral wind perturbations. This is because during the daytime, the ionosphere is mainly affected by the E-region dynamo effects. The E-region conductivity is very large during the daytime. So the neutral wind perturbation in the E-region will impact the ionosphere. But during the nighttime, it's mainly due to the F-region dynamo. So that's the reason why this neutral wind perturbation shows very similar patterns compared with this vertical e-cross-speed drift perturbation. So this shows some evidence that this neutral wind perturbation related gravity waves actually can induce electric fields and seed those plasma bubbles. So this supports the gravity wave wind dynamo hypothesis. So again, here shows a snapshot that's showing that the electron density variations at different UT time. So you can see very clear, we call this upwelling structures or large-scale wave structures. So, and the bubble developed from the crest of these upwellings. And when you compare the bottom panel here that shows this is a vertical e-cross-speed drift. So interesting is that we also identify very clear vertical e-cross-speed drift enhancement here. And this doesn't happen very often because this occurred during the midnight. Usually, as I mentioned earlier, that the pre-reversal enhancement is considered to be the driver of radiator instability. And pre-reversal enhancement of vertical drift mainly occur during the post-sunset. So around like 18 to 20 local time. But this this midnight vertical ecosystem drift occurred around like 23 to 1 local time. So this vertical drift enhancement will push the ionosphere to like a higher altitude and facilitate the development of these upwelling structures. And also, you also can notice that there are also very strong vertical equal speed drift perturbations embedded within these upwelling structures and plasma bubbles. So this also can be observed from the CNAV satellite observations. But first, I want to mention that what's the source to induce this midnight vertical equal speed drift enhancement. So if we really compare with the Formosa one here, yeah, this just shows an example that, and you can see where this is ion density, it shows very significant plasma depletions. This is comparable with our simulation results. And this is a vertical drift. You also can compare with the simulations. It shows that bubbles, plasma bubbles shows very distinct vertical drift enhancement. But before the bubble development, you also can see some small scale equal speed drift oscillations. So this is likely related to these upwelling structures here. So this demonstrates that even though this occurred in the bottom side of layer, we can use the in situ satellite measurements to detect the equal speed drift in the top side ionosphere. So the in situ measurement can be a potential source to potential tool or to detect this kind of structure. So I want to mention that what's the source to cause the midnight vertical equal speed drift enhancement? As I mentioned earlier, that the tsunami can generate conjugate effect, and because the neutral wind perturbation induce the electric field and mapping along the field line to the conjugate hemisphere. So in this case, the midnight vertical equal speed drift enhancement is also related to the TID neutral wind perturbations. So here that shows the zonal wind perturbations as a function of longitude and latitude. So you can see very clear like a westward wind and eastward wind perturbations here. And this westward wind causes this. This is a zonal equal speed drift perturbation. So during nighttime, because nighttime the wind is usually eastward, but this event shows that this west wind causes some westward equal speed drift, and also like a vertical equal speed drift perturbations. So yeah, this is the zonal and the vertical equal speed drift as a function of latitude and the altitude. So if you compare with this neutral wind map, it's at about like 95 degrees in longitude here. So this westward wind perturbations generate this significant equal speed drift perturbations along the field line. So you think that this is so-called conjugate effect. This neutral wind perturbations here will induce electric fields and transmit along the field line to the equatorial ionosphere and push the ionosphere to higher altitude. So yeah, so from the model, we also can observe this kind of conjugate effect. So, so as I mentioned, then the next question is that we know that these polarization electric fields are induced by these westward wind perturbations, but what causes these westward wind perturbations? So I will skip this one. It's a solar terminal waves. Yeah, so, and solar terminal waves is like a large scale waves driven by the migrating tides. This from this paper. But I won't go into detail about this because of time, but this figure just shows the simulation of solar terminal waves from the SD wave mass. So you can see the solar parameters here, the day and the night, and you can observe very distinct large scale V structures here, the black dashed line here, and the white line here shows the white dashed line here shows the westward wind perturbations. So these perturbations likely are related to solar terminal wave. If you compare the observations from Chou satellite, this is from Forbes paper that's showing the neutral density perturbations. So during the sunset or sunrise period, you can identify the neutral density here. It's just very large scale perturbations. So these large scale perturbations induce electric fields and greatly impact the ionosphere background conditions. So then it provides an ideal condition to trigger the plasma bubbles. So finally, I think I do not go to these two events, but I just want to mention that today I want to talk about this event shows that some continuous distribution of plasma bubbles. But actually, bubble shows very significant day-to-day variability. So you can, if you compare these plasma bubble structures with the button here, just the neutral imperturbations, you can find that the distribution, the spatial distribution of bubbles actually are affected by this the wavelengths of these gravity wave perturbations. But interesting that during this day, we do not observe any bubbles, although you still can see very significant gravity wave perturbations. That's because of the background condition. So yeah, but yeah, so I think, so I just want to mention that the day-to-day variability of plasma bubble is very significant and very difficult to predict. So the further work is still necessary to further understand how these waves impact the ionosphere and the plasma bubbles. So yeah, so I will go to the conclusions that in this talk, I talk about the ionosphere response to the 2011 Tohoku tsunami induced gravity waves. So we find that the TID driven by the reflected tsunami waves, this is the first time we can observe that the tsunami, reflected tsunami actually can continuously impact the ionosphere for over 10 hours. So, and the tsunami-induced TID display very similar wave patterns to the tsunami oceanic waves. And also for the first time, we observed that the tsunami caused ionosphere perturbations in the conjugate hemisphere through the conjugate effect. So this is much faster than the tsunami waves. We know that the tsunami, when you propagate from Australia, from Japan to Australia, it will take about 8 hours. But through the conjugate effect, the perturbation almost occurs simultaneously. So, and we also investigate the role of convective gravity waves on the bubble development. And we find that gravity wave seeding actually is very critical for bubble development. And we understand that the zonal scales of the gravity waves can affect the spatial distribution of plasma bubbles. And the electric fields generated by these waves actually can mapping along the field line to the equatorial ionosphere and facilitating the bubble development. So from this work, we understand that actually the joint ground-based and the space-bound GNS observations is very useful for like a tsunami detection and warming. So, but of course, we only have very sparse observations, especially in the ocean region. So observation and modeling works are still necessary to advance our understanding of how those lower atmosphere waves impact the space weather. Yeah, so yeah, that's pretty much all of my today's talk. So yeah, because of time, I cannot go very detailed, but yeah, so if you are interested in these talks, you can just go to these papers. It will show more detail. So thank you very much.
So thank you, Dr. Zhou, for such an engaging talk. So I think now is the time for the QA. Does anyone have any question? And please feel free to turn on your microphone and ask to Dr. Zhou. If not yet, I have one, maybe two questions. So first, given the multiple sources of the gravity wave, so how can we distinguish between those generated by the meteorological system and those triggered by the seismic or the tsunami events in the observation data?
Okay, actually, we know that gravity waves actually they can reflect the source. I mean, for the tsunami, okay, you can see that the tsunami. You can see my screen, right?
Yeah. Okay.
Yeah. For example, like a tsunami, actually, you can display like planar waves or concentric waves.
Mm-hmm.
So you can easily identify that from this source that if they are planar waves, they usually can generate planar TID. But if they are concentric waves, they can generate concentric TID. But for the like thunderstorms, they are usually like a point source.
Oh, point source.
So yeah, so they usually can generate like a concentric waves and propagating upward to the upper atmosphere. But it's not always show. It doesn't always show concentric wave patterns in the ionosphere because the gravity waves will greatly impact by the background winds. So sometimes you only can see like a partial winds. For example, like a super typhoon Miranda. One of the reasons, of course, because of the limited data coverage. But from this event, you can see that sometimes we only can find that you only propagate northwestward. But if you have more dense observation, like in the US, you will see that like this is the tornado events here. You only see like wave propagating northward, but southward is not very clear. One reason probably because the background wind can be like a southward during this time. So it filters out the southward propagating gravity waves.
Okay, thank you. So, just other curious, the photo you just showed that photo by the Jeff Dye, right? And with the concentric rings in the night sky. So are those actually gravity waves that we can see with the naked eye, or is that something?
No, I don't think you can see those waves in the naked eye.
So,
but I think the most easy way to see gravity waves is that the mountain waves. I think it's because Taiwan, so many mountains, right? So sometimes you can see there's some stationary waves related to mountain wave. Yeah.
So it's not a visible light photo, right?
Yeah. You need to use some.
Okay.
But I'm not expert of the camera, so I don't know how to capture this photo.
So how often can we actually observe something like this? It's very quite easily.
I think we have I do not show the slides here, but we use we have studies using the satellite.
Yeah.
The VZ is like a airborne images on board the International Space Station.
Oh, airborne.
So
okay.
We can this one is a VZ. So we can, but this is like we collect like a 3-year data from 2012 to 2015. So we can calculate the occurrence rate of these gravity waves. So it shows that the occurrence rate of these gravity waves is around like 40 to 50%. Yeah.
Wow, that's really interesting. Oh, it's your paper, right?
Yeah, this is submitted. Yeah, so it's still under review. So yeah,
under review. Okay, sure.
Yeah, invest the connection between the gravity waves and the plasma bubbles.
Yeah, I'm looking forward. Thank you. So, any other question for Dr. Zhou? I think Dr. Zhou is an expert in the gravity wave in Taiwan. So, if you have any question, please feel free to ask. Any question?
Yeah, not necessarily. Yeah, you can ask me any question if you. Yeah.
But no worry, if you have any question, you can ask Dr. Zhou directly, or you can send the question to the TSU, and we can transfer the question to Dr. Zhou. So if no, I think that it's about the time, and it's the almost 11 o'clock in your end, right? Yeah. So let's once again thanks to Dr. Zhou for today's talk. And please feel free to visit the TSU website and get the latest update and on the upcoming seminars. So thank you all for joining us today, and we look forward to seeing you next time. So thank you, Dr. Zhou. Thank you again.
Thank you.
谢谢，感谢，辛苦你了，辛苦。
OK，对，谢谢。
好，拜拜。